Okay, so we are live on YouTube. To answer the question that Mariam has asked, there is at least a classroom web page where you can at least get the material. I don't know if you can communicate between yourselves, but at least you can probably see who you are and share the contacts. I think that should be possible. Anyway, otherwise organize in order to interact for the presentations or the projects. This said, let me share the screen. This is the slides that I want to share. Okay, so today we are talking about something that we have mentioned during several previous lectures, which is the use of memory, and in particular of experience replay, and how this is related to multi-goal reinforcement learning. So also in this case, we'll start by looking at what we know already, so what we already discussed briefly, and then we'll move from there and see how all these things connect. So we have mentioned several times in previous classes that in off-policy reinforcement learning algorithms, most commonly in off-policy reinforcement learning algorithms, sometimes also in on-policy algorithms, but mostly on off-policy algorithms, we use replay buffers. So a replay buffer is nothing else than a sort of database where we store some information. Specifically, the information that we store in the simplest version of the replay buffer is a transition. So the replay buffer is composed of several transitions that are experienced by the agent. And these transitions are inserted in the buffer while the agent is executing some policy in the environment. And then they are sampled from the buffer at training time. So every once in a while, when we decide that we want to update our policy or value function, then we sample some information from, we sample some of these transitions from the replay buffer, and we use them for training. So the replay buffer is characterized by mainly two factors, let's say. One is the capacity, which is the total number of transitions that we can store in the buffer. And the other one is the age of the transitions, which is the number of training gradient steps that we take since the transition was generated. Okay. Now, a transition in the simplest case, again, is nothing else, just to repeat that, it's just the state where the agent executed some action, the action itself, the reward that it collected, and the new state it ended up in. Okay, so this is the simplest thing. And why do we want to use this? I think I've mentioned this in some classes before, but the idea of using a replay buffer comes from the inner structure of the reinforcement learning problem, because the simplest thing would be to avoid using such a buffer and then just train with the samples that we collect by interacting directly in the environment when we get them. Now, this is somewhat problematic if you're using a function approximator, because typically function approximators make the assumption that data that you're training with have this IID property, so they are independent and identically distributed. Clearly, this is not true anymore, because if you're training on state and actions that generate new state, then there is a clear relation between these things. So the idea of using a replay buffer comes from the fact of dealing with function approximators, dealing with the fact that we assume IID data, and the fact that we want to cast the reinforcement learning problem in order to use, for example, neural networks more in a supervised learning fashion. This is one motivation. The other motivation is the fact that we're using off-policy algorithms often when we do this kind of when you use this kind of memory. And since we're doing that, we want to be efficient in the data that we use, because we can reuse this data as many times as we want, and we want to be able to use them multiple times and reduce the collection costs. So the collection cost means that we don't have to run our agent several times to collect the very same data, but just sample from this experience replay now in order to train with them. So the typical training loop when we have such data structure involved in the training process is the following. So we have our agent, which is executing some policy. So by means of this policy, it's sampling from the environment. So it takes the action, it executes in the environment, taking a step in the environment. So it samples a new observation, and then we store this information in the replay memory. And then from this replay memory, we sample a random batch of transitions. And then we optimize the policy network, the target network, the value network, whatever we have. We do that how many times we want. And then after that, we choose an action from our policy. This is partially, what I just described is partially true because oftentimes you take several actions with the same policy without optimizing. So it's not said that every time that you store some information in the replay memory, then you optimize. Actually, most of the time it's not like that. But this is to give you more or less the idea of the process. Now, when I say that we randomly sample from the replay memory, from the replay buffer, this means that we use some probability distribution in order to do this sampling. Typically, you do uniform random sampling, and this is fine, but it's not always what we want. So this is what the authors of the paper prioritize experience replay, for which again you find an implementation from Google in here, in this link. The idea that I had was very simple. Why should we randomly sample when we have instead some transitions that are somewhat more informative for us? Because we want, and now I read by citing them, we want to more frequently replay transitions with high expected learning progress as measured by the magnitude of the temporal difference error. So if we have a high TD error, this means that there is high potential for learning there, because we can perform more updates on this data and then improve our performance. So the idea is very simple. The implementation is less so, because using prioritization based on simple temporal difference error can lead to, first of all, a bias, which we'll discuss a little bit more in detail in a few slides. And the other thing is the loss of diversity, which means that we are sort of reducing also the maybe this is not the appropriate way to describe that, but we're losing some amount of exploration. If we focus too much on prioritized data, we are just focusing on them, so we lose the diversity of the data that we collected, and we don't explore as much the state space that we actually visited. Okay, so there is a solution to this, which is using stochastic prioritization. And the solution to the bias that they think of is using importance sampling, but we'll see this more in detail. So let's say we don't use stochastic prioritization, but we just want to correct, set the priority of our sampling by means of this temporal difference error. This is called a greedy approach in their paper. And this greedy approach, basically what we do is we pass through all the data that we have in the experience replay, and we store the magnitude of the temporal difference error in each transition. So we compute the TD error as we normally do. So this is the standard formula for computing the TD error. This is specifically in the Q-learning fashion. And then in our replay buffering, instead of having only ST, AT, RT, and ST plus 1, we also have the magnitude of this TD error. Now, this is quite expensive because every time you update the Q function, then you need to recompute this TD error, and you need to re-update every value that you have in your experience replay, which is very costly. And the experience replay typically contains a lot of data, sometimes millions of transitions, and this is not, I mean, it's probably feasible, but then the cost of doing this is very high because you're calling several times this Q function, and then this slows down the whole process a lot. So the solution that they think of is updating by sampling and only update the items that we just sampled. So we do some sampling, we sample a batch from this experience replay, and then we update the priority based on the TD error only of the samples that we just have in our batch. So this is a stochastic approach, which solves also the diversity issue that I was discussing before, because now, I mean, we did some sampling. We don't have every priority set in a very accurate way. So this diversity problem comes maybe in a reduced amount. So, okay, so we say we do this sampling, we update the TD error only for these items that we have in our batch. Sounds good. What do we do next? We need to compute the priorities given the TD error. The authors of this paper, of the prioritized experience replay paper, propose two alternative approaches to compute these priorities. One is a rank-based method, and another one is a proportional method. In the rank-based method, we basically sort the items based on the TD error, on the magnitude of the TD error, and then we assign a priority based on this rank. And in the proportional method, instead, we just assign a priority which is proportional to the magnitude of the TD error plus some epsilon, which is to ensure non-zero priority. If we have new samples, then we initialize the priority at maximum value so that we can look at them more often, which is kind of intuitive as well. And then, given these priorities, we need to compute the probability of sampling the data from this experience replay. How do we do that? We simply divide the priority of the item that of the data point that we're looking at by the sum of all the priorities. And as you see here, there is an exponent, which is alpha, which is basically the factor that determines the level of prioritization. So if you have 0, then this means that there is no prioritization at all, because this probability becomes all the same. So we're doing uniform random sum. Okay. Okay. As I said before, priorities can introduce a bias, and this bias arises again from the fact that we are setting the priorities while we are collecting the data and we are using them and we are training on them. So this means that we are changing the distribution that we're using for our updates. So this means that we will be focusing more and more on the on some data based on the information that we have in our Q function, and sometimes this can be over focused, so introduces this kind of bias. The solution here is very simple, which is the one that we already know from off-policy learning, which is using important sampling for updates. So we introduce these weights that basically tell us that if the probability of a certain item or the certain data point is becoming 0, then the weight becomes large, because we know that we're not going to sample that data point very often. So we want to give strength to this information in our update. Of course, if the probability of selecting that data point becomes very high, then since we know that we're going to see that data very often, we don't need to give a lot of weight to this information. Also because if we sample that data very often, that data point very often, this means that we have a high error in the information that we have in there, so we shouldn't update with very high weight on that. Finally, if the probability is around 1/n, where n is the number of data points, then this means that we have some sort of uniform sampling, and then the weight becomes 1. So every data point that we sample has the same importance. Here, beta that we use in this computation for the weight of the importance sampling simply defines the amount of correction that we apply. So how much basically this weight is important. So here you see that there is the pseudo code of the double DQN with this prioritized experience replay, and simply they do what we just described, which is we store transitions, then we sample a transition according to this probability set on these priorities, then we compute the importance sampling weight in the way that we just described. We compute the TD error, and for this data that we have in our replay in our batch, we update the transition priority, and then we do the update for our networks. Here they use 2 Q networks because it's double DQN, but it's the same thing as what would be for DQN. Now looking at the results for this double DQN, without prioritized experience replay, so with uniform sampling probability, with rank-based method for prioritization, with proportional method for prioritization, then we see that the performance of the prioritized experience replay is much higher, and not only is much higher, it also converges to a better result much faster. So, for example, so this uniform approach goes to 100% score, but it goes to that much slower compared to the one with the rank-based or proportional methods for prioritization. Now, I don't see a very distinct difference between the rank-based and proportional methods. I think they I'm not remembering this exactly 100% correctly, but I think they say that the proportional method works better, but I'm not 100% sure. Anyway, from this from this plot, this is not visible. But yeah. Okay. Now, I decided to, given that we're talking about replay buffers, I decided to talk in this lesson instead of the next one about reverb. So reverb is a framework that has been released by DeepMind for experience replay. You see here there is the paper and where they describe the inner mechanisms of this replay buffer and the link to the GitHub. Now, I said I could have talked about this also in next class, because Reverb not only is an efficient and easy to use data storage system, but also it works for distributed reinforcement learning, which is the topic of the next and final class. But anyway, given that we're talking about the experience replay right now, I think it's good to talk about it in this class. Reverb not only supports the experience replay, but also different data structures for first in, first out, last in, first out, and queues and other things. So if we look at the schema that we have here, simply we can have multiple DQN actors that collect our data in a distributed fashion. Then we send by means of a server client mechanism our data to the Reverb server. Then this Reverb server stores the data in some way that we'll see just now. And this data is then sampled by the learner in order to perform the training. So nothing else than what we just described, but stored and implemented in an efficient way that is ready for you to use. So I think it's important in a course like this to also look at practical things that can come to help when it's needed. So just to say, you don't have to use this only when you are working with in a distributed setting. You can use this also in your single processor on your computer. You don't need to do anything. You don't need to be doing anything particularly fancy in order to use Reverb. And I think it's quite a good implementation that you should consider adopting. So. In particular, data in Reverb are stored in some chunks that belong to a chunk store. So these chunks are then referenced by items that belong to some tables, the same tables that you can think of in a normal database. And the tables control the sampling and insertion request. So if we have this kind of data here, then you see that this is agglomerated in a single chunk which has this key, and where A, which is the key of this tensor, is compressed to store both items that come in sequence, and similar for B. Then every item just references the chunks, so it tells us what are the keys of the chunks that we should be looking at, and the chunk contains and stores pointers to the data. This is the architecture of Reverb. So there is a client, one or more actually clients on different processes eventually. that create a sampler and a writer. They communicate with the server, of course. And this server stores the tables that contain the items that point to the chunks that are stored in the chunk store, and the chunks preserve the data. But more importantly, the tables have two selectors and one rate limiter. So the selectors can be of two types, can be a sampler or a remover. So a sampler is used to select the items when they are requested by the client. So it does exactly what you would expect that to do, sampling data. And the remover is instead used to to select the items that need to be removed from the table when the table is full. These selectors can implement different strategies. For example, a first in, first out, a last in, first out, and also the sampler can be uniform or prioritized, as we have just seen. So I think that's why I wanted to talk about this now. I think it's very well connected to what we just described. So if you want to implement a uniform, so a standard replay buffer, or prioritized replay buffer, experience replay, you can just use Reverb and it's ready to use for you. Then there is the rate limiter, as I said, that controls when we can insert or sample new data from a table. Okay, so a very simple example for implementing a replay buffer here. If we want to implement a replay buffer in our code, we simply import Reverb. Then we create our server. The server has a single table in this case. You can have more tables. And we set the name of the table. We say that the sampler is a selector, a uniform selector, and the remover is a FIFO, first in, first out selector. The maximum size of the table is 100, and the rate limiter is minimum size 1. Okay. Then in the same, like here, you can have other things happening or not, but simply you create your connect, your client, which points to localhost port 8000, and then you are done. Okay, so this is as simple as doing this, and we can look at some of these plots that I think are interesting. So this is a plot of the performance of the server for inserting data. This is for sampling data. So if we have to sample these different sides of information, this is the performance that we get. As you see, it doesn't change a lot with the number of clients. So if there is not a lot of growth in the amount of clients that are connected, which is something that is quite good. And this is true both for sampling and insertion. So you can do basically the same amount of queries per second. Either you have 50 clients or 200 clients, more or less. It's working the same for example, data size of 400,000. Okay, so now you have an idea of how to. So why should we use an experience replay, and how can we prioritize our sampling, and how we can implement such things. That's nice, but typically reinforcement learning algorithms are quite sample inefficient. So even if you have these experience replays, then you have to sample, you have to insert a lot of data. They have to be quite big replay buffers, and you have to sample the same data several times in order to get anything good, especially for complex problems. So this is why the authors of this paper, Neural Episodic Control, introduce this new approach that is based on differentiable neural dictionaries. So here you again find a link for the for GitHub, which is not an official GitHub, but still a valid one. So I said I have written in this slide neural episodic control, also known as sample efficient memory, because this approach aims at reducing the sample complexity of reinforcement learning algorithms that also rely on memory. Then they do it in a slightly different fashion from typical replay buffer, how you would think of. And they get inspired by this, the notion of episodic memory that typically contains only specific experiences that then can get reused based on what you're doing. Again, this approach that they propose is based on differentiable neural dictionaries that, at least for some of you, and I'm referring to Biagio here, you should be aware of as you are using that for your research in slightly different way, but related. So the memory that is used in a differentiable neural dictionary is composed of two arrays, which are K and V. K is the array of keys and V is the array of values. They are dynamically sized, but also equally sized, meaning that K and V have the same amount of vectors in it. So K and V store some vectors that represent, again, the keys and the values of our memory. And we can perform simply two operations with this memory, which are lookup and write. So how do these operations work? So for lookup, we simply compute an output of our lookup by means of a weighted sum of the contents of the V array. So basically, every vector that is contained in the V array contributes in some amount, depending on the weight that we compute here, we'll discuss briefly, contributes anyway to the final output of this lookup. Now, the weights are computed based on the query key. So the query key is used to compute some sort of distance between the each key that is contained in the memory, in the key memory, and then normalized sort of by dividing by the sum of all the distances that we have. So K here is nothing else than a kernel function that is telling us how different these keys are. Okay, so this distance in this kernel space. And so the distance, so the difference, the similarity actually between the keys is used to compute the weight, and the weight tells us how much each item in the memory of values contributes to computing the output. So this is a simple way to do a lookup in this kind of memory. Writing occurs basically after every query. So we query with some key h, and then we add h to the key key arrays, and the output that we just computed from this lookup we add in the value array. Okay, so why do we want to do such a thing, which is kind of apparently is kind of weird? Why do we want to use something like this? This is to more efficiently reuse our data. And this is the pseudocode of the neural episodic control algorithm that basically preserves a DND, differentiable neural dictionary, for every action that belongs to the action space. Right? So for every action that we have in the action space, we have such a dictionary. And then every time we collect an observation from the environment, we project that into some embedding that is the space of our keys. And then we look at the memory, this memory that we just described for each action. And we estimate the Q. So basically the Q value is what is stored in each memory for each action. So the values that are stored in this DND for each action is the Q value of that action, based on the observation that is projected in this embedding space, which is then used as the key for the lookup. Okay. Then this is it basically, because after doing this, we simply perform an epsilon grid, execute an epsilon grid policy based on the computed Q value, and then we take this action, we collect our reward, and we store this new information in the memory of the action that is actually selected, and we also store the transition in our buffer to select another mini batch. So this is more efficient in the fact that we are reusing information that is projected, not only projected in this embedding space, but also we are sort of using a support vector of all the information that we previously collected in order to build on that and check what are the similarities of the between the new sample that I got, the samples that I already saw, and I can efficiently compute the Q value directly from that. And so this is the main power of this approach. And in fact, results by looking at by implementing this kind of approach are quite promising, because if we look at the learning curves on different games like Hero, Alien, Pong, Mrs. Pac-Man, you see that neural episodic control is obtaining a much higher performance compared to all the other algorithms with a reduced amount of frames compared to the other ones. So eventually, for example, for Pong, DQN and other algorithms reach the same performance, but neural episodic control reaches this performance after only 5 million frames, and instead DQN needs 5 times more amount of data. And this is true also for other games, as you see here. So this is very much pointing in the direction of the sample efficiency, which basically tells us that using information previously stored in the past and building on top of that by means of this sort of support vector is a powerful idea in reinforcement learning. Okay, so we just discussed about how to become in some way more efficient by means of using not only the replay buffer, but also some other memory inside our reinforcement learning algorithm. So we have started by saying we need to replay buffer. We can be prioritizing more important data that we know that we are making more mistakes on. Now, if we want to be more efficient, we need to be having some other memory that helps us in computing our estimates of the Q function. So far, so good. But sometimes you just have environments that are too bad with you, because they don't help you at all, because the reward is too sparse, so you never see any reward at all. So even if you have a powerful prioritized replay buffer, you have a neural episodic control approach, like where you have this kind of memories that do all of that, still you cannot get anything out of it, because you have zero signal at all. So let's watch this video together. And this is a video from 2 minutes paper, which is 2-minute papers, which is a series of videos that where they explain some sorry, I don't know what's going on here. How can I get out of it? Okay. Yeah, they explain some papers that came out quite recently, and I'll let them talk for this introduction to the Hindsight experience we played, and we'll talk a bit more about that. Is it starting? Okay.
However, imagine having a really careless teacher who never tells us the points but would only tell us whether we have failed or passed. No explanation, no points for individual tasks, no telling whether we failed by a lot or just a tiny bit. Nothing. First attempt, we failed. Next time, we failed again, and again, and again, and again. Now this would be a dreadful learning experience, because we would have absolutely no idea what to improve. Clearly, this teacher would have to be fired. However, when formulating a reinforcement learning problem, instead of using more informative scores, it is much easier to just tell whether the algorithm was successful or not. It is very convenient for us to be this careless teacher. Otherwise, what score would make sense for a helicopter control problem when we almost crash into a tree? This part is called reward engineering. And the main issue is that we have to adapt the problem to the algorithm, where the best would be if the algorithm would adapt to the problem. This has been a long-standing problem in reinforcement learning research, and the potential solution would open up the possibility of solving even harder and more interesting problems with learning algorithms. And this is exactly what researchers at OpenAI try to solve by introducing Hindsight Experience Replay, HER, or HER. In short, very apt. This algorithm takes on problems where the scores are binary, which means that it either passed or failed the prescribed task. A classic careless teacher scenario. And these rewards are not only binary, but very sparse as well, which further exacerbates the difficulty of the problem. In the video, you can see a comparison with a previous algorithm with and without the HER extension. The higher the number of epochs you see above, the longer the algorithm was able to train. The incredible thing here is that it is able to achieve a goal even if it had never been able to reach it during training. The key idea is that we can learn just as much from undesirable outcomes as from desirable ones. Let me quote the authors. Imagine that you're learning how to play hockey and are trying to shoot a puck into a net. You hit the puck, but it misses the net on the right side. The conclusion drawn by a standard reinforcement learning algorithm in such a situation would be that the performed sequence of actions does not lead to a successful shot, and little, if anything, would be learned. It is, however, possible to draw another conclusion, namely that this sequence of actions would be successful if the net had been placed further to the right. They have achieved this by storing and replaying previous experiences with different potential goals. As always, the details are available in the paper, make sure to have a look. Now, it is always good to test things out whether the whole system works well in software. However, its usefulness has been demonstrated by deploying it on a real robot arm. You can see the goal written on the screen alongside with the results. A really cool piece of work that can potentially open up new ways of thinking about reinforcement learning.
Okay, so I think you got the intuition. Let's look at some details regarding Hindsight Experience Replay. And here I'm saying HER, also known as Memory for Sparse Reward Setting, where we are now extending our standard replay buffer to deal with the sparseness of the reward. So let's look together at this pseudocode, where basically in every episode we sample some goal, where basically we extend our MDP to also include these goals on which the reward function depends. And we also have a strategy for sampling goals. So we sampled some action conditions on the goal that we just not only on the state but also on the goal that we just sampled. We execute the action, we sample a new state, and then we do this until termination or until the max length of the episode has been reached. And then we look at all the rewards that we have specifically for not only state and action, but also specifically for this goal. And we start the transition in our hindsight experience replay. Now the transition contains not only the state, the action, the reward, and the next state, but also, and also here there should be a done flag. But anyway, this is not relevant to the purpose of this discussion. But in addition to that, the state is always concatenated to the goal. So this is more or less what you would do in the standard experience replay, except that now you are concatenating your sampled goal to the state itself. Then what you do is you sample a set of additional goals for this replay. And then for each goal, you compute the reward and you store also that transition. So the reward that you would get by executing this action with this goal and adapting, of course, the reward to the goal itself. So this is the hindsight experience replay part, where we also replay the transitions that we just collected, also conditioned on other goals. Okay, so we sort of do a replay based on what would happen if we were looking at another goal instead. And based on that, we store other transition in the replay buffer. And then we do our standard thing, which is sampling a mini batch from the replay buffer and then performing some updates. So this is pretty much straightforward. Now, there is one question that might arise, which is, okay, so if we do this sampling now, we have in our transition not only the rewards, but also and the states and the actions, but also the goal. How do we use that? The answer is, we'll see in a second. So give me one slide to show you how using hindsight experience replay is better in this kind of setting compared to other approaches, and then we'll see how to use the goal in training. Okay, so if we compare a standard DDPG, DDPG plus count-based exploration, and DDPG plus hindsight experience replay, we can see that the performance that we get by using hindsight experience replay is much better. And this is specifically, this has been specifically used a lot for some complex robotics tasks, like, for example, pushing, sliding, pick and place to be learned, using reinforcement learning without any reward shaping. So there is no information that we get at every signal, but not just success or failure, like the video before was describing. So if you run standard DDPG with that, you need to be ending up in a state where you have failure or success, more importantly success, in order to improve and get some improvement in the performance and train and continue progressing towards the final learning of this task. But if you don't have that, just doing some exploration, like we described, for example, in the first class, can help, but might be not sufficient. And a very useful thing is that of using this goal-based approach, where you basically divide your task in subtasks that allow the agent to collect some information more easily, and then based on that, perform much more complex tasks. Okay, do you have questions till now? If not, in order to train with goals, and for example, also in the Hindsight experience replay paper, they use universal value function approximators that basically introduce multi-goal learning. These are particularly useful also when you are dealing with general value functions, generalized value functions that are used for performing forecasts. Forecasts in reinforcement learning are basically queries that we do on conditioned on some policies. But anyway, the thing that you need to remember about this is that you can categorize that as some sort of multi-goal learning. And also in general, in the Hindsight experience replay, you need some multi-goal learning. If you need to do that, you can use this universal function approximator, which is nothing else than an approach where the Q function not only receives the state and the action, but also the goal as an input. This can be done, however, in different ways. Of course, the benefit of this is that if you have the goal coming as an input to the neural network, then you can generalize between different sub-goals. You're conditioning on the goal, but you can generalize between different goals. You can do that by means of different architectures. The first one, which is the one that you find here on the left, is the concatenated one, where you just concatenate the state and the goal. You pass that through the neural network, and then you get your value for the state and the goal. And then there is the other approach, which is a two-stream approach, which is more factorized, where you map your state and your goal into some embedding space here by means of these psi and phi functions. And we'll see how to do that now. So the concatenated approach is basically an end-to-end training approach, and it's very simple, meaning that you just pass the goal as well as an input, and you do that, and you do your training as you would normally do. For the factorized approach, for the two-stream approach, you have a two-step learning, where you first build a data matrix of sub-goal values, sub-goal and values, and then you factorize it in order to compute the target embeddings, right? So you can compute this target here. So you train your functions to predict this target, and then you train directly the network in order to predict the V. So in the paper they suggest that this approach, this second approach, works better, and the results show this as well. But I think, in general, you can use either. I think if you don't have good results by means of the concatenated approach, you can try the two-stage one. But otherwise, I would suggest, if you have to do something like this, just go for the end-to-end approach to start, and then for a more complex one. So, so this is a plot that I find quite interesting of the results that are obtained by means of a universal value function approximator trained only on goals in the first three rooms of this maze, and then generalizing in such a way that it can achieve also goal in a different room, which is the fourth one. So here, as you see written in this description, you visualize the learned universal value function approximation for three test goals that are marked as red dots in the fourth room. And this is below. You see also the country, and as you can notice, this is quite working well, and it's interesting to see how it's easy to generalize between different universal value, different rooms, by means of this universal value function approximator. In general, here you see also a generalization to unseen values, and this is based on the rank approach. Okay, so I think this is it for today. I don't have other topics I wanted to discuss, unless you have questions, and I would like to give you some time to ask questions regarding this stuff. But yeah, otherwise, I think we're good to go. Any question?
Just one question about the organization of the exam.
Sure.
I was wondering if you have already a list of papers that we can pick up, let's say the papers for the exam.
Sure. So
okay.
Before doing, yeah, I will publish that during this week on Classroom directly. I think the question that I have is how many of you are interested in doing a project, because the other ones will do a presentation. So is there anybody who is interested in doing a project in order to count for the right number of papers to propose? So nobody's thinking to do a project. Okay, sounds good. Okay, then I'll post that on Classroom, and yeah, then you will be able to choose by means of some form. Maybe I will create a form in order to let you choose the paper that you want to present. Yeah, that's it.
And what about the exam date? Will be the last day of the lecture, or you will define another date for the exam?
So we'll find another date. I expect that to be the Monday after the last lesson. But we can adapt based on the needs of everybody. If you have other courses or things that need to happen on that Monday, we can post a survey again to select the best date for everybody for the exam. I would lean towards the Monday after the last class. So if 24th is the last class, then the 31 of May would be a good date for me.
Okay, thank you.
Just recall that we have also another class that is starting this week, so that will last also the next Monday, I think. Maybe others will confirm.
Sure. I mean, as I said, I will post. I mean, I will set a tentative date, and then you can comment on Classroom, and we can decide together what's the best. Okay?
No, it's fine. Just to remind.
Okay. Sounds good. Other questions? Okay. If not,
I have a question.
Sure.
Maybe as a project idea, since I'm working on a paper, could be that I can present the paper.
Let me stop this.